And this time we finish, and just I repeat how the MOSFET's channel does work, and then I will continue what the MOSFET itself will look like. So we have started with the MOS, we have started with the metal oxide semiconductor interface by saying that the work function in the metal is equal to the one in the semiconductor. Therefore, if you don't apply any voltage, we have a flat band condition without any band bending. And then we said we have some oxide, and over the oxide, if we want to charge this capacitor, we have to deploy charges at both ends. And deploying charges in the metal is a matter of fact that it is infinite thickness of the deployed charge area, infinite low thickness in the deployed charge area. But for the semiconductor, we need some area to deploy charges. And if it is the space charge region, then we can calculate from the Poisson equations that the space charge region has to have an infinite thickness, and there we have a finite num. Yes? Oh, hey, yeah. Sorry about that. Great, thank you. Um, Good point. Okay, so rewind, play. Okay, rewind, play. Uh, so the text I said, the flat band condition is due to the work function equalness. And to deploy some charges to the capacitor, we have to, in the metal, it's effortless. It is an infinite low thickness. But in the semiconductor, we need some space charge region to deploy these charges. And the charge density is given by the doping concentration. So therefore, the doping concentration level here is missing. By the way, here is missing the line. So that this is the space charge concentration. And we learned that the amount of charge is proportional to the square root of the surface potential you have due to the charges. Okay, if you increase the voltage, whereby you connect the positive and the negative poles of your voltage source that way, you increase the bending due to the fact that you have a surface potential, and this bending causes a cross section of the intrinsic level with the Fermi level. And if you cross the Fermi level to the intrinsic level, then you have the Fermi level closer to the conduction band than to the valence band. So this condition starts to generate a so-called inversion layer. Inversion because here your free carriers are holes, and here at the interface the free carriers are electrons. And if you continue this banding, you have the strong inversion. And the strong inversion has a defined crossing of the Fermi level and with the intrinsic level. The defined crossing value is the Fermi level distance is equal now to the conduction band edge. Or if you define it with the energy, the voltage difference between the intrinsic to the Fermi level, then this distance from intrinsic to Fermi is equal to this distance, but from the other way around. Okay? So this is the definition of the strong inversion. So in the definition of the strong inversion, we have therefore 2 times VIF as a bending. Okay, and if we know this, we know the amount of charges in the space charge, because if we know the bending, we know the voltage we apply. And this voltage applied to the semiconductor defines the width of the space charge. And if we have the width of the space charge, we have the charge in the space charge. And therefore, we have the voltage over the oxide, because if we have the capacitance and if we have the charge, we have the voltage. And this voltage overall is defined as the threshold voltage. So this threshold voltage is the one which generates an electron C, a sea of electrons, which has the same concentration like you have had for the holes in the bulk. Okay, so therefore we have derived the threshold voltage as a surface potential, which is given in as a charging value for the capacitor, and the surface potential. The surface potential is here, and the charging value is here. So it is the sum of these two values. And if you further increase now the voltage across metal to the bulk semiconductor, then you assume that this space charge doesn't increase further, because it is far more easier to generate here the electron negative charge compared to the space charge, because this amount is proportional to the e to the power of the applied voltage. And this charge is proportional to the square root of the applied voltage. Therefore, a slight increase in the bending in the surface potential exponentially increases this amount of charge. So the overall Q here, the increase of the overall Q is, given by this equation. It's an exponential equation. And therefore we say, and define that the space charge no more increases, and the space charge width is the value you have if you have this type of bending. And this type of bending is 2 times VIF. Okay, so we have the assumed maximum penetration of the space charge. And we have the assumption that then the charges we need is given by this C. Therefore, we have here this peak just there, just at the interface. Yeah. In reality, you do following. If you increase the voltage, let's say, to this value, okay, you have increased the voltage, then following happens. You have almost the same bending. Oh, no. Almost the same bending. And I have to switch to gray now. So you have increased the voltage here. you have increased in the same way here. You have almost the same bending, and the additional applied voltage is consumed at the oxide. Why? To have a larger voltage over a capacitor, you need a larger charge, amount of charge. And this larger amount of charge is generated by a slight increase in the bending, only a little bit, because the density increases with the voltage exponentially. So you need a slight increase in this bending, which causes a large increase in the charge. But this slight increase in the bending also proportional to the square root of this slight increase also slightly increases this base charge boundary. And there we say it doesn't increase anymore. Exactly. And this is given here. So the width increases proportional to the square root of the bending, and the density of the charges increases to the e to the power of the voltage of this bending. So therefore, you need a little bit more surface potential to generate the charge to consume the additional voltage. And at that point, we say, I don't care about this exponential behavior because we haven't cared about this Q and this amount of bending here. We haven't cared about that. Therefore, we say the capacitor is just switched on if we apply a voltage called threshold voltage. And after if we increase further the applied voltage between gate and semiconductor, we just charge the capacitor as we would have metal here and metal there. That's it. In the if you go to integrated circuit design, then the MOSFETs can be used the following way. 1 second, I'm just preparing how to sketch it. So this is the gate contact. Let's assume this is the source. Let's assume this is the drain. You combine them to one node, and then you have a capacitor, and that's the oxide capacitor. Exactly. So you use these MOSFETs as very large capacitor or very large sheet capacitance because this oxide thickness is usually lower than 7 nanometers. And in the case you go to our master course at our research center, it's now called Electronics and Drives. Further, before it has been called Robert Bosch Research Center. And in our Electronics and Drives Center with the Leistungs- and Microelectronic Master courses, we teach you to design an integrated circuit using that stuff. Okay, so your idea is perfectly correct. It is heavily used in integrated circuits, Mr. Botta. Okay, so like you said, we switch on the capacitor, and if we have a more voltage, then to switch it on, we call it overdrive voltage, and this overdrive voltage generates our charge in the capacitor. Okay. Yes. Let's continue to take a look on the real structure of the complete MOSFET because up to now we have had just taken, oh, two more people are coming in from Turkey. Uh, Hello, Mr. Sulak, and hello, Mrs. Akbal. Hi. Uh, One comment I have given to the rest of the students, I have asked them whether you are willing to evaluate these courses because I have this semester also the chance to make an evaluation, and you are the people to do these evaluations about my courses from many aspects. Is it okay that we do that next week? Great. And Mrs. Akbal, again, your question, please. During the lecture time, I will distribute an login token so that the evaluation is anonymous but individual. So each of you get a token, you log in, do the evaluation. I don't know who has given which evaluation. It is anonymous, but I have overall an impression from different aspects to my course. So I intend to do that next week. Okay, great. Thank you. So let's go back to the MOS structure. If we have a low doped P substrate, so who has asked? Yeah, Mr. Rausha, yeah, exactly, low doping. And Mr. Sulak is painting something at the wall. My children also. No, I'm kidding. So, Mr. Rausha, you said, what about this doping level in the substrate? Yeah, we know now it is a function. It changes the threshold voltage, and if we have a p-type, the crossing 2 times VIF, we just switch on the channel. We can make it vice versa. We can make also a well, which is low n-type doped, so donator doped. And VIF is then the vice versa crossing. And if you do that, the crossing here generates a channel of a p-type. So you can invert both doping concentrations. So therefore, we have an N channel, electron channel MOSFET, and we have a P channel, hole channel MOSFET. And you can do this side by side on one silicon. Therefore, this is the reason why. So the co-integration of N and P-type MOSFETs onto one silicon substrate has made this career in the industry for silicon. Why is that so important? The NMOS has potentially its source lower than the gate. The PMOS, every signs are inverted by multiplying with minus. So the source is higher than the gate. Therefore, you can switch now. Now I'm just painting, drawing uh, a very common circuit uh, in integrated circuits or also in power electronics. It's a half bridge. This is a p-type and this is an n-type, for instance. You can control this gate source of the p-type. Let's say this is 5 volt, this is 0 volt, it's ground. and you control this gate source with here your control circuitry and here. Now you can switch on you can switch this node to 5 volts if you connect here a certain threshold voltage. Let's assume your control voltage is 2 volt, and you can switch down this node to 0 volt if you apply here the 2 volts. Therefore, you can fully control, actively control potential in a circuit. This is not the case in bipolar transistors. The N-type bipolar transistor, it is an NPN, we haven't learned it, but it will come, is very fast, it's great, you can make gigahertz circuits, but the PNP bipolar transistor is very slow. It's not usable in the same frequency range. Not all, even not in the vicinity of the same frequency range. Therefore, if you do a circuit in a bipolar transistor technology, the only device which switches this node towards the 5 volt is if you just do here 0 volt, then the transistor is switched off, and then all the parasitic capacitance of this node. So this node has a parasitic capacitance to ground. All this capacitance needs to be discharged through this resistor. And this is damn slow compared to actively shortcutting this node to the power supply. Therefore, digital circuits, yeah, not really. You can't do that with bipolar. Analog circuits, we will learn, is the domain of bipolar, but digital is the domain of MOSFETs. Therefore, you have also technologies not only integrating PMOS and NMOS, but also additionally MOSFET bipolars. These technologies are called bi-CMOS, bipolar CMOS, so bi-CMOS technologies. But that's just a story. Let's come back to the lecture. We define the so-called gate length by the distance of these contact areas. That's the effective gate length. You, as a designer, you draw this gate length by putting this metal as a layer. You are the designer of these layers in the circuit diagram. And in the technology, due to the undercut, we learned why it has happened. Due to this undercut, the drawn length is reduced to the effective length. Okay, why we call this L length, whereas this width is larger than the length? Because your electron transport is happening alongside this length. So the channel's working distance is this length, and the working width is this dimension. Therefore, this naming. Okay, so if by nature, now you take a look at this sketch and you see if I make my transistor wider, I have more paths for the electron, so the resistance drops. like on the motorway. Wider motorway, lower flux resistance here. Okay. Um, Now let's talk about the P well. So let's talk about this contact. Why you need this? I have a source, I have a drain, I have a gate, and let's start. But why you need additional bulk content? Bulk content. The reason is here. We apply a voltage between metal, it's called gate, and the semiconductor, semi. But where is this semiconductor? It's here, but there is no contact. You know, you have to control the backside of your transistor with this bulk. And usually, let's go to the circuit diagram. And usually, you contact this bulk to the lowest potential you have in your circuit. Assuming you have here a shortcut and this one is the ground. Therefore, you can say the bulk is connected to ground due to this contact area. In reality, you have a certain potential difference, yes, but we neglect this potential difference, okay? Just connecting the bulk with the ground, you assume you have here 0 volt. Okay, now we have here a 0 volt in the bulk. Well, why this is important? Because not only for the controlled gate bulk, because you then, if you don't control here, you don't have a controlled threshold voltage. So therefore, you would not know when the transistor switches on. First thing. Second thing, we have here a very stupid configuration which has happened. You see this unintentionally generated, but a present of the technology for you. And you haven't ordered this present. It just kits you in the application. Why? If the bulk potential, if the bulk potential would be higher than the drain potential, then this body diet, it's called body diet. Then this body diet, it's not the body as a friend, it's the body of the semiconductor, is forward biased. And this forward biased condition is given here as a diet, put it here. So if you have a silicon transistor and if you have a how it's called discrete If you have a discrete transistor, you buy a silicon transistor, it's an N-channel one, then internally this bulb is already connected to the source. You can't change that. You have three wires on this discrete transistor you have in your hand, so three wires. And this transistor has a body diode. So if you reverse polarize, if you put this drain down and source up in the potential, then you can use your transistor as a diode. And very often you don't want this diode because if this diode happens to have a forward current we learned, then you inject holes into the space charge region and you inject electrons into the space charge region through the space charge region to the other side. Don't forget these conditions. Go back to the slide which I'm talking at this moment. The slide I'm talking about has been shown you on page, yeah, on page 59. There I said, if you forward bias a p-n diode, you inject electrons, and these electrons generate, an injected value of density of devices, of particles, and these particles generate a so-called charge. No, discharge, diffusion charge. So this diffusion charge is placed into the substrate of the MOS, and this charge kills the function of the MOSFET. And therefore, you have to prevent this condition. And usually, you do this in circuits by, so if you want to prevent this diode to be forward biased, what you do in silicon to prevent this diode to be forward biased, you put an additional physical real diode in parallel, real as a device, but a Schottky one. So tell me which side I have to add a line to get a Schottky. I don't know. I have to take a look all the time if I have to draw a Schottky. Okay, Schottky. The, the left one? At the bottom. Okay, but left or right? Zener has two, but Schottky has one. But which side? Right or left? Ah, Zener is here. Na, 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 na. Okay, and the Schottky has it like, yeah, exactly. So so we have so if we draw it this way around, this one is up and this one is down. Okay, so we do that now. Mhm. So by intention, I'm not remembering it to do this game in all my lectures. So this one up and this one down. And if you have a physical Schottky diode in parallel to the unintentionally produced body diode, this one takes over the current, and this one has no diffusion charge due to the fact that it is a Schottky, and therefore it's fast. Okay, so this is a side topic. Let's come back again to the main topic. The PMOS has the same unintentionally generated diode. Also, one is here, and the other one is here. So now, if you put the drain above, no, below, one moment, the drain is all the time at the negative side. 1 second. Do we have done an error? Drain is up. No, it's okay. So the source is up and the drain is down. This is the error I have made. You have to wire the source and the bulk together. This was my error in my drawing. Sorry about that. If you have to connect the bulk also to the source, but now the source has the highest potential on your circuit diagram. So it's called VDD. Hmm? And this source potential has the highest value you can have in your circuit diagram, in your circuit, your integrated circuit. And now if this drain compared to this source, if this drain is higher than the supply voltage, then your diode is forward biased. And you do then at that point the same game. You have here between the source and drain a diode like this, and in externally on your PCB you put in a Schottky. In the case of silicon MOSFETs, something like this. Okay, but if you go towards 600 volt applications, now it starts to be very interesting. It's just a story, not the lecture. If you go towards 600 volt applications, then you can use, for sure, MOSFETs also for 600 volt applications. But you don't have anymore a silicon Schottky diode to prevent to switch on these diodes. Therefore, you have a trouble because in 600 volt applications you have, for instance, an electrical engine. An electrical engine has spiral inductors called the coils in the engine to generate the torque. And these inductors force the potential higher and lower than the supply limits. And therefore, you can't use MOSFETs. You have to use the so-called IGBTs, insulated gate bipolar transistor. IGBTs I've shortly introduced in my third semester lecture called Electronics, but in German. And these IGBTs, they don't have reverse current conduction possibility. If IGBT goes with its drain above its supply voltage, then it is just isolating. And for the IGBTs, you can now choose to connect the appropriate diode in parallel. Cheap applications, they use a fast silicon bipolar PN diode. A little bit more expensive applications, they use silicon carbide Schottky diodes. But silicon carbide Schottky diodes, they have a higher voltage to have a certain current level. But silicon carbide Schottky diodes, they don't have the diffusion charge. Therefore, it doesn't mind that you have an additional voltage needed for the forward bias of the diode. Because if you reverse bias the diode, you don't have to deploy all the diffusion charges injected into the diode because there is none. It's Schottky. Okay, so this is just a story for power electronics. Therefore, I have just put here the P will to the ground and the N will to the highest possible potential in your circuit. And now you say, well, that's a fact. Let's check the fact in the internet. Take an IC, take a operational amplifier. Go on your own to the web when you have some spare time, or if you have just a willingness to do that, in let's say in DigiKey, and take an operational amplifier from let's say analog devices, and then just take a look to the pin which is called output, and this pin has a specification. All pins have a specification. Take a look at the output pin. Usually the output is something like this. And this pin has a specification that it is not allowed to be higher than 0.5 volts, usually, than the supply voltage. Now you know why. Because if it is higher, then an non-negligible amount of current would flow through this body diode. And this need to be prevented. And then the specification says you are not allowed to have values higher than 0.5 volts. That's it. Okay. Now let's go to the so-called operational regions. I hope my son is opening the door. Let's see. Dennis! No, he's sleeping. I have to open the door. One moment, please. I'm just stopping the record thing. No, he is going. Okay, great. I haven't have to stop. Okay, the operational regions of the MOSFET is you have a gate source voltage, and if the applied voltage is lower than the threshold voltage, we say it's switched off because we have no channel. Point one. You can apply a drain source voltage larger than 0 volt and you don't have a current flow because you don't have a channel. Okay, so switched off region. The second region is called linear region, or also it's called triode operation. I have to accompany my son to the door. 1 second, please. Perhaps I have to give a sign. I'm back in 1 minute. Okay, so I continued the recording. We are waiting for something to be delivered, but it's large, and my son was not very comfortable for the decisions the guy wants to make. So I have to jump up again, perhaps later, when he has managed to carry up all that stuff to the door. I apologize for this interruption. It was not planned. Okay, so we have a linear region. If, now it's important, if the drain voltage is lower than the value of the overdrive voltage. I repeat. First, your gate voltage is larger than the threshold voltage. This means the overdrive voltage is larger than 0. Again, what is the overdrive? This is the value above the one of the threshold. So if you apply a gate source voltage larger than the threshold voltage, then you have a certain overdrive. You have a certain channel, the inversion layer. Okay. At the same time, if the applied voltage to the drain is lower than the overdrive, assume the overdrive voltage is 1 volt. Assume the threshold voltage is 0.8 volt. This means your gate source voltage is 1.8 volt. Then your drain source voltage needs to be lower than 1 volt. Lower than this overdrive voltage. Why is this the case? If I want to have a full electron C connecting source to drain, then I need a C, an electron C here, and also here. But this region, by intention, I have put this area, this drain, outside the screen area. This area looks exactly the same like this area. Now, if this potential is at 1.8 volt, and if this potential is at 1 volt, what is the potential difference crossing this area? It's 0.8 volt. That means threshold voltage. So if I compare it like doing the following stuff. If you higher up your leg, you squeeze up. If you higher up your leg, you squeeze the potential. One moment, I have to increase my picture. Here I am. If I increase my leg, then I squeeze this potential difference. And if this potential difference between metal and this doped area, if this potential difference is lower than 0.8 volt, then you have no channel. As it is the case, now I make it smaller again, as it is the case here to the source, because the MOSFET doesn't know that you called this area source and this area drain. The MOSFET doesn't know that. It's symmetrical, usually. Okay, and this in turn means if you want to have an inversion layer here and here, you have to fulfill this condition. Okay, well, let's go to this sentence. This is a very important sentence, and therefore I have set this sentence into this box. And it says, with gate source voltage is equal to the threshold voltage, a channel is just formed. Okay, we know this. Any further increase of this applied voltage above the threshold, which is called overdrive voltage, it has a name, this above value, increases the carrier density of the inversion layer. Okay. Now, when the drain source voltage reaches the value of the overdrive voltage. Because the drain source voltage is the voltage between drain and source. And the overdrive voltage is just a value which appears between gate and source. Therefore, I say value. The channel is pinched off, it's squeezed out at the drain end, as there the effective gate bulb voltage, which I tried to point out here with my fingers, just reaches the threshold value. Okay, so be aware that a transistor's channel is pinched off at this end if this potential difference reaches the threshold voltage. And this happens if you apply a drain source voltage is equal to the overdrive value. Okay, so I have many times repeated, now I stop repeating it. Now we will use it. This point in the voltage diagram is this point where the drain source is equal to the overdrive and the gate source is larger than the threshold one. So at this area, we have our V overdrive, which is larger than 0. And this at this point, the V overdrive, so for this MOS, is exactly 0. Okay? This is the area where you leave the linear region and enter the saturation region. Okay, now let's go to the saturation region itself. First, physically. What does mean saturation region? It means nothing different for the gate. As usual, you apply no theory. 1.8 volt, you apply. And now the drain source voltage is larger than 1 volt. I need coffee. Okay, if the drain source voltage is larger than 1 volt, then the gate drain voltage is lower than the threshold voltage. Yeah, sure. And if this is the case, then you have a certain point in this channel where you just have V threshold. Okay? Because if this voltage is smaller than V threshold, and if this voltage is larger than V threshold, then you have a certain point in the area where the voltage is exactly V threshold. For sure, it has to happen. And now let's assume that here you have 0 volt and here you have VDS. Okay, so we have here is 0 volt and here we have 1.8 volt. No, how much? Larger than 1. Let's say, one moment. 1. I want to have here 1 volt. And we have here 0 volt. Then we can say we have here 1.5 volt. Okay? So it's roughly linear. And the person is just coming again and pressing the doorbell. I apologize. Um, I stopped the tack. Well, now we have the condition that we apply a drain source voltage of, let's say, 1.5 volt. This voltage drops alongside the bulk. At one point in the area in between drain and source, we have just 1 volt. And if we have 1 volt, we have exactly V threshold between gate and this position. Therefore, we draw this pinch-off point at this point. And at this point, we have the full voltage of 1.8 volt. So here is 1.8 volt, and here also 1.8 volt. The only thing which changes is within the bulk, which is seen by the channel. Okay. Therefore, we have a so-called saturation region. Now the question is, how on peep Earth is this electron is going from here to there? How does that happen? In the C, in the inversion layer, okay, I jump into the inversion layer. This inversion layer is a so-called resistor. And through a resistor, I can flow. No problem. But now, here we have the P region. And we have an electron P connection. It doesn't work. But we know from measurement it works. But we haven't understand it at this moment, how it works. Now let's start to draw some additional stuff. We say the drain is 1.5 volts. Okay? And the bulk, assume that here your bulk is also 0 volt. Let's assume it. So the bulk is 0, your drain is 1.5 volts. So this diode is reverse biased. What do you know about a reverse biased diode? It has a space charge region which has penetrated towards the silicon. It is increased. So we have a certain space charge region, certain depletion region. Now it starts to be interesting. In this space charge, the electrical field is this way. And what happens with an electron which goes into this space charge? It is antiparallel, so electrons drift antiparallel to the electrical field lines. So the electrons which enter this area drift to this contact, and within this contact, this contact is a resistor. It is conducted normally conducted to the ohmic contact. That's it. That means you have an electron here. We have a parasitic resistance here. This parasitic resistance just changes to be an inversion layer resistance. So an inversion layer is also a resistor full of electrons. And the electron which happens to enter this electric field drifts through the electric field to this contact. And exactly the same happens in the PN diet. Where does that happen? One moment. Go towards page 58. There I said, I have a space charge region. And in the space charge region, if the electron which is at the boundary happens to enter the space charge, it drifts to here. Therefore, the space charge, therefore the minority carrier concentration, the electron concentration, drops to 0. And exactly this happens also in the MOSFET. So the electrons which are at the boundary of the space charge region under the gate, so the electrons which are at the boundary to the space charge region and happen to reach it are sucked out to the contact. Now, you have a limited amount of electrons. You can just catch them up and bring it to here. Therefore, the amount of current is constant if you further increase the drain potential. So the current doesn't increase anymore because you have a certain amount of electrons available to go through the space charge. Like with the saturation current. If you reverse bias a PN diet, the saturation current is limited by the amount of minority carriers which are available. Now, your current is limited by the not minority carrier concentration, but with the inversion layer concentration. That means if you increase your gate voltage, if you increase the inversion layer concentration, then you increase the drain current and you get these output characteristics. So here we are in the triad region, it's the linear region. So it is like a resistor. Higher voltage, higher current. In the first approximation, these are straight lines. If you come over, if you go over this point is VDS is equal to V over drive. I just write it again in real pencil colors. Here the VDS is equal to V over drive. Then your channel is pinched off at the drain end. At this point, the channel is pinched off at the drain end. If you further increase the drain voltage, the pinch-off point penetrates towards the source. And this means you increase the drain voltage, but you don't increase anymore the current. Okay? Is this understandable at that point? If you further increase the gate voltage, if you further increase the gate voltage, you further increase the density of this inversion layer. If you increase this density, you increase the number of electrons which can be transported towards drain. Therefore, you increase the drain current. And in reality, should I explain it now? No. Don't care about this slope at this moment. It's too much. It's overload, I think. I'm not assuming it, but if I would be a student of mine, I would say, okay, that's all. Stop here. I need a break. Okay. Hey, thank you to be honest. That's great. Then, if it is the case, because we are free to do whatever we want with our time, we say we make a break, okay? Let's say we make a break of uh, till 2 o'clock. Great. I'm hungry. Let's see us again at